It's my pleasure to introduce Davide, Ravotti, and with the first lecture in reviews, we'll be talking about time changes of Horocycle.
Thank you for coming. So today I want to continue talking about time changes of Horocycle flow. So last time we introduced them, so let me quickly go over what we did last time. We are in our usual setting where we are looking at compact quotients of SL2R. The Haar measure is invariant for the classical Horocycle flow. And now we wanted to perturb this flow. And the way we did it was by keeping the same orbits, but changing smoothly the speed at which these orbits are perturbed. So we fixed the positive function alpha, normalized to have integral 1. And we perturbed the vector field. U was the vector field generating the classical Horocycle flow. So we perturbed it by multiplying it by 1 over alpha. Alpha, again, is a positive function. So the picture that we want to keep in mind is the following. So we have our Horocycle flow, our nice homogeneous flow. And now we are rescaling the tangent vectors in a non-constant way, but smooth. For me, alpha will always be sufficiently smooth. And we want to study this flow. So today I want to talk about the ergodic and mixing properties of this type of perturbations. And then next time, maybe we'll start also today, I want to address a natural question that maybe you already have in mind, is who tells me that these flows are actually different flows from the original one. Maybe we are in a point where more sufficiently smooth perturbations are actually conjugated to the unperturbed one. So maybe if I'm smart enough, I could find a change of variables that translate me this flow into the previous one. So next time we will study this problem. But for now, I want to look at the ergodic and mixing properties of this flow. So last time also we noticed that since the orbits are the same, moving for time t with the time change will correspond to moving for some other time with respect to the unperturbed flow. And we found some nice expression for this tau. So this, recall, was an additive cocycle over the time change. I'm going a bit fast because we saw this last time. Found a formula for it. And from this, we deduced that the difference between tau, so the parameterization of the orbit with respect to the homogeneous flow, and with the time change was sublinear if our space is compact and the time change is sufficiently smooth. And we saw the proof. So today I want to start talking about ergodicity and mixing. So in order to start talking about ergodicity, the first question is with respect to what measure, right? We need to have an invariant measure to do. And so the invariant measure, I will make a guess and I will prove that this is indeed an invariant measure. So vol was the Haar measure, and now I'm considering another measure which is equivalent to the Haar measure by adding a density, and the smooth density is going to be alpha. So this is so alpha was strictly positive, so this is an equivalent measure to with respect to R. And also notice that by my normalization, that was the integral of alpha with respect to the R measure was 1, this vol alpha is a probability measure. So the first thing we want to prove is that indeed this measure is invariant for the time change and is also ergodic. Other questions? Okay, how I will sketch a proof of this lemma. How do we prove that the measure is invariant? Well, one way to do it is to prove that so I want to prove that this measure over here, so alpha times the Haar measure, is invariant by the flow generated by the vector field 1 over alpha times u. So saying that the claim about invariance is equivalent to saying that if I take the Lie derivative of this, so this is a nice differential form, I can take the Lie derivative of this form with respect to this vector field is 0. so the definition of the d derivative in the first lecture of one vector field with respect to the other, but the definition of the d derivative of a differential form with respect to the vector field is analogous. So the d derivative is telling you if I push this form by the flow generated by this vector field, how it's changing infinitesimally. It's giving you the infinitesimal change of this object over here. So if the infinitesimal change is 0, it means that this form is going to be constant when I move it via the flow generated by this vector field. So this is the equation I want to prove, and you can prove it in some way. One way is use so-called Cartan's formula to unpack what this object is, and if you do it, you see that this d derivative here is going to be equal to the d derivative of the R measure, so without the density, with respect to the Horocycle flow without the. And the reason is that here you have alpha and here you have 1 over alpha, so they cancel out. Nice. And so in the first lecture, that indeed our measure is invariant by the Horocycle flow. So this d derivative is actually 0, so that this d derivative is 0, so that the flow is preserved. The measure is preserved by the flow. Okay, so we proved that the measure is invariant. Why is it ergodic? Well, orbits of a flow and time change are the same. So if I have a set which is invariant for a time change, is also going to be invariant by the unperturbed flow, because the invariant set contains all orbit, is saturated by orbit, so invariant sets are the same. And this measure is equivalent to the R measure. So if a set has measure 0 for the R measure, it will also have measure 0 with respect to this measure. So invariant sets are the same and null sets are the same. So ergodicity of one is equivalent to ergodicity of the other. And the Horocycle flow is actually unique, the ergodic even better. So this is going to be ergodic as well. Does this make sense? So we know that this flow is ergodic with respect to this measure. So maybe we can say something about the ergodic averages as well. And I want to see that the same estimates that we found for the unperturbed Horocycle flow are going to be true as well for time changes. How do we do this? Well, essentially it will follow by a change of variables, but let's do it slowly. So last time we proved, so tau, recall, was the parameterization with respect to the unperturbed flow. And we proved that its derivative with respect to R, the time parameter, was going to be precisely the value of the density of the vector field, or the perturbed vector field. So 1 over alpha at that point. It kind of makes sense. Okay, so let's now take a sufficiently smooth function, say C4, and let us fix T to be greater than a constant. I don't care exactly what constant it is. So I want to estimate the ergodic averages of this function with respect to the time change of the Horocycle flow. And the trick, I want to apply a change of variables. So the trick I do is multiply and divide by the value of alpha at this point, h tau rp evaluated at p. Okay, so if I multiply and divide, well, 1 over alpha at that point, I would write it as the derivative of tau with respect to tau r with respect to r. And the other term, I leave it as it is. So it's going to be alpha composed with h of tau rp evaluated at p. And then I factor it with f. So this is going to be alpha times f composed with the flow times the derivative of tau. Now I have exactly a nice, I can apply a change of variables, right? So my new variable is going to be tau of r comma p. I have the derivative already. So this average over here becomes 1 over t, the integral from 0 to tau of the function alpha times f composed with the unperturbed standard Horocycle flow.
Yeah, but alpha inside disappears.
This alpha over here? No.
Yeah, so if you, okay, so.
So from here to here, I multiply and divide it by alpha composed with HT divided by alpha composed with HT. The 1 over alpha is rewritten as this guy over here, and then I'm left with alpha.
Sorry.
Does that make sense? So I wrote 1 equal to alpha divided by alpha. Yeah. Is it clear? So I'm left with this integral, and now I can apply the results that we proved in the second lecture to estimate this guy. So if I were to take the average of this function here, so 1 over tau, the integral from 0 to tau of this function over here, well, this would converge to the expected value, which is alpha times f, and the error is going to be polynomials in the extreme of integration. So the difference between this average to the expected value being the integral of alpha times f with respect to the Haar measure, because here I'm taking an integral with respect to the unperturbed Horocycle flow. This is going to be bounded by some constant, the C4 norm of alpha times f, and tau to the tau of TP to a negative power that here I call gamma is our usual 1 minus nu naught over 2 that we saw the other times. Okay, and so we are basically done. So what we obtain, okay. So here, from this formula here, I multiply and divide by tau of TP. So what I'm left with is that, and also notice, sorry, this integral of alpha times f with respect to dvol, I can rethink of it as the integral of f with respect to the invariant measure for the time change. So what we obtain is that the ergodic average of f with respect to the time change flow minus the expected value is going to be tau over t times some constant times the C4 norm of alpha times f and the negative tau of TP to the minus gamma. And now I can use some brutal estimate that we proved last time that tau is proportional to t up to some constant. So this tau over t is bounded by some constant, the constant being the maximum of alpha over the space. And same in here. And I can also use the fact that the C4 norm is multiplicative. Okay, so if I can write the C4 norm of alpha times f as bounded by some constant times the C4 norm of alpha times the C4 norm of f. So up to increasing the constant that it will involve all these terms over here, we can prove that the deviation of the ergodic averages for the Horocycle flow are basically the same as for the unperturbed Horocycle flow. And to attribute this was proved, I think, first by Ford and Ulchigrai in 2012. Okay, so yeah, for the sufficiently smooth functions. So this kind of tells us.
So your comment on the C4 norms is to remove the alpha in this last.
So yeah, okay. So here I could have actually written some other constant a times just the C4 norm of alpha, because usually I'm happier of statements of this form where the deviation of the ergodic average is going to be constant times some norm of the function involved times a negative power. Yeah, okay. And this tells us mostly everything we wanted to know about ergodicity. So now we want to say something about mixing, because mixing is less clear than ergodicity. And so in order to prove mixing, we are going to use the same argument that we saw in the third lecture. So this mixing via shearing, because the advantage of the mixing via shearing argument with respect to the proof that we also saw by Ratner is that it's geometric in nature, and so it generalizes very nicely to these situations where the homogeneous structure of the flow is not present anymore, but the geometric shearing properties are, we will see, are still there. Okay, so the first step was what I had called the mixing via shearing lemma. So let me restate it in this setting. So assume that you have two C1 functions and take one of them f with zero average. Then for any positive s less than 1, we can bound correlations of f and g at time t with some constant, the C1 norm of g, and then this term over here that I think of it as equidistribution of the curve phi x of s pushed by my time change flow. Okay, so and the lemma that we saw in the third lecture was for any transverse curve, and here I'm already taking geodesic curve because I want to apply it to geodesic segments. Okay, so we proved it for the standard Horocycle flow. I quickly sketch a proof for the time change because it's slightly different, but I don't want to spend too much time because it requires some modifications, but not too many. So how does this work? Okay, for the classical Horocycle flow, the first step was to use invariant with respect to the invariance of the Haar measure with respect to the geodesic flow. So this time we have this measure vol alpha. So the first thing I want to do is rewrite it as, so f composed with ht times g with respect to vol alpha. I will rewrite it as the integral of f composed with h alpha t times alpha times g, right? Alpha is the density. But now the integral is taken with respect to the Haar measure. And I like this because now I know that the Haar measure is invariant by the geodesic flow. So I can compose everything in the integral with the geodesic flow. So for any, this integral over here is going to be equal to this integral over here for any fixed sigma because of invariance of the Haar measure for the geodesic flow. And if this is true for every fixed sigma, it's also going to be true if I take an average between 0 and capital S for any capital S positive. But I will choose capital S to be smaller than 1, and we will make a specific choice later. So I rewritten my correlation as an average of the same quantity, but pushed with the geodesic flow in front, or sometimes sigma. And now I want to do again the integration by parts that I did last time. I'm not going to repeat it and use the Cauchy-Schwarz inequality. So these steps in the middle are the same as what we did in the third lecture, so I'm not repeating them. And what we obtain after applying the Cauchy-Schwarz inequality is that the correlations can be bounded by the L2 norm of this function and the L2 norm of its derivative with respect to this this flow over here that comes from doing the integration by parts. So this is going to be the bounded by the L infinity norm. I mean, they are bounded by the L2 norm, but I can bound it by the L infinity norm of alpha times g and of the derivative of alpha times g in the direction of the geodesic flow. And this term over here being the supremum over all short segments up to length s of the average of f along the pushed segment, the pushed geodesic segment pushed by time t with respect to the time changed flow. This was the same principle as last time. Okay, so this is a constant. We are happy with this, so now we want to prove that these pushed segments equidistribute, and this will not only prove mixing, but if we can prove how fast they equidistribute, so how fast this norm goes to 0, we can give an upper bound on how fast the mixing is happening. And I will point out two things. I will repeat them. Let me say it now. So this lemma allows me to bound the correlations with respect to the L2 norm of this function over here. But we will be more greedy and we will prove it. We will prove an upper bound for the L infinity norm. So we'll prove it uniform bounds for this quantity because the setting allows us to do so. I forgot what was the other thing I said, so maybe it'll come back to me. Okay. Yes, the other thing is that I wanted to say is that we are already choosing the transverse segment we are pushing to be geodesic segments. And if you remember what we discussed last time was that for the standard Horocycle flow, so if here you don't have a time change, the mixing rates that you can prove are not optimal. So a natural question, so this will give us some rates, but then the natural question would be, are these rates optimal? And the answer is, we don't know. As far as I know, it's unknown whether the mixing rate for a time change depend on the time change. So the upper bound, the bounds that we have come from a method like this, that for the unperturbed Horocycle flow do not give us the optimal bounds. So we don't know what are the optimal mixing rates for time changes of the Horocycle flow. So you see, it's a very, I mean, a priori, it's a simple perturbations that we are doing. And yet, some question that is quite natural, and maybe one of the first you should ask, which is what is the mixing rate for a flow like this? We already don't know. So even when
did I understand correctly that you will ask that rate of mixing, which you can prove is the same as in the unperturbed situation, or
no?
No.
No. What I will show is prove. I mean, give an upper bound of this mixing rate by bounding the equidistribution of geodesic segments. But and this gives us an upper bound. And then in the third lecture, we saw that if alpha was constant, this strategy will not give you the best bounds, because we noticed that segments that are non-geodesic, that are transverse to that, gives us better bounds. So I do not think that we should expect that the rates that we get from this approach to be optimal. I do think they probably are not optimal.
Here you have to use, in a sense, geodesic would be effective. Or not.
I don't know if I have to. I will do it because then I can do all the calculations. But I do think that if we were to try to repeat the argument with the transverse segments, at least a priori, we should get better bounds. But it's less clear for reasons that will appear later. I think it's a good question to try to address, but it's still open. So, okay. So what we need to estimate is this, which is the equidistribution of pushed geodesic segments with the time change. And again, instead of estimating the L2 norm, I will estimate it pointwise. So what we did for the unperturbed Horocycle flow, maybe I'll try to draw a picture over here. So recall that this was starting from a point P. For the standard Horocycle flow, if I go up to e to the s times t of p, it's the same as here I could take my geodesic segment, move it up to a cycle flow composed with s. And this was closed in the quadrilateral, so that in the unperturbed case, if I take this geodesic segment and I push for time t, so this point go up to here, to get very close, I should move it for e to the s times t, but here I'm pushing only for time t, so this point stays behind, so I get a shearing like this. For the time change, I will have some similar picture. But what we will see, so here I will have h alpha t composed with this and here I will have my h alpha t of p. So the image of this curve is still going to be somehow sheared, but it's not going to be a nice straight line. So I should expect to see something smooth, but not nice as in the unperturbed case. So it will be, so the main, I mean, so if I just look at the support of this curve, I think it will still be close enough to a long piece of orbit, but it would be parameterized in a hard way. like in a non-trivial way. Okay, so the first thing I want to do, and it's similar to what I did for the classical Horocycle flow, is replace this red curve with this segment, this orbit segment over here. So if I do want to do the commutation, so if I push the geodesic segment for the Horocycle flow, so here I use the time t, so I want to use the commutation relation I know for the unperturbed Horocycle flow and the geodesic, so I rewrite h alpha t of this point as h of tau t at this point over here, the same point. And now compose with the geodesic, and now I commute the two. So I get phi x s composed with the Horocycle at time e to the s times tau of t at the point phi x s t of t. Okay. So again, if I think of this segment, this geodesic segment to be sufficiently small, then I can remove this phi s. So my average over here along the pushed geodesic segment, I can bound it by an integral where I integrate from 0 to sigma of f composed with this term over here, so just the Horocycle component. And the error I'm committing is basically going to be of size of by the mean value theorem is going to be bounded by the C1 norm of f times the distance, which is at most s. So that when I take the average, it's going to be capital S. Okay, so I reduced the integral of f along the pushed segment with an integral of f along the support, like the support of this guy is going to be again some Horocycle orbits, but now the parameterization is messy. It's not something. So in the standard case, we have e to the s times t. Now we have this. Okay. So now I'll make my first choice. So I will take s to be very small in t, such that I can neglect this term over here, and I'm just left to study this term. Okay, so I will want to prove some polynomial bound. So I will choose my capital S to be t to the minus some gamma over 2. So that the first term over here, I can ignore it, and I can just reduce myself to bound this term. Okay, and so what if I just do simplify notation, if I call Ts the point in the geodesic segment at distance s from P, I have to bound this integral, which again looks like a Horocycle orbit, the support at least, but the parameterization is not the usual one. It's a complicated one. And so the key quantity that we want to estimate are these two objects over here. So this is the parameterization that I need to understand. So I will call the shear to be the derivative of this function with respect to s, and the distortion to be the derivative of the second derivative divided by the first derivative square. Okay, so what are these two quantities? So the derivative of this with respect to s is going to tell me how much the segment gets sheared, right? So the bigger the derivative, so if you imagine that the distance between the initial point and the end point is going to be bounded by the length of the geodesic segment I'm pushing times the derivative at some point. So bounding the derivative, understanding the derivative is telling me how shear this segment is going to be. This term over here that I call the distortion is telling me how far is this parameterization to be linear. It's a measure of how non-linear is this parameterization. So if this parameterization was linear, this guy would be 0, because this guy would be 0. Is it so? Well, anyway, so the smaller this guy is, the closer to linear this parameterization is going to be. So these again, let me pause 1 second because, okay, we are doing this proof of mixing via shearing for time changes of Horocycle flow, but this technique can be applied to many other smooth parabolic flows. So when you don't have some homogeneous structure, but still you want to prove mixing, this mixing via shearing argument is a way of, once you have shearing, to improving ergodicity to mixing. And so you take some transverse direction, you flow it with the flow. If you see that it approximates some long orbits, then you can upgrade ergodicity to mixing. But the key point is trying to understand how the segment you are pushing differs from a flow orbit segment parameterized in the natural way. So you want that when you push a transverse segment, it really gets long in the direction of the flow because you want to see equidistribution. So it needs to approximate a long orbit segment. So you need this quantity to be large. And at the same time, you want the parameterization not to be too wide. You want to be sufficiently close to linear. And this is controlled by this term here that you can think of it as a distortion coefficient. Does that make less sense? Because this is the maybe the point of this lecture. Okay, so the estimates that you can prove, but I'm not going to prove them because they are a bit.
Or can I ask?
Yes.
So, is control of just shear would be, so if I'm not interested in mixing rates, would the control over shear be enough to show mixing, or I need also to know the distortion?
No, you also need to have some control on the distortion. Because maybe if you just look at the image of the segment, it looks like a long orbit, but maybe your parameterization, you go very fast at some points and then you slow down a lot in some other point and then you go very fast. So it's not going to be equidistributed, even though the support of the curve looks equidistributed. Maybe you will spend an incredible amount of time in some small portion of the space. So I do think you need some control on the distortion anyway. Does that make sense? No?
Can I ask a question? So I tried to compute these two notions for unperturbed situations. So in unperturbed, tau is equal to t.
Yeah.
So the derivative with respect to s of exponential function is the same.
Mm-hmm.
And if you take the next, this distortion formula, and you differentiate, you will not obtain zero.
The point PF is not.
You will get something small.
Yes, small. Yes.
Small is good enough. Because also in the unperturbed case, it was not really linear. So the parameterization was e to the s. So in the I like it.
Some error which was
so in one, so the parameterization in the unperturbed case would be e to the s times t, and then in one step in the proof that I did was remove e to the s and write it as 1 plus s, and then there was an error. So also in that case the distortion is not zero, but it's good enough so that it doesn't cause you a problem. Thanks for the question. Yeah. So the bounds that you can prove is that indeed the first derivative, so the shear, is going to be linear in t. So it's going to be bounded both from above and from below by t times some constant. That we would not really care what the constant is. And the key point, and in some sense is a bit the magic of this argument, is that the distortion is of order t to the -1. And the proof is really just computation. So you just have to be patient and differentiate this object and use the formulas that we had for tau. So t being equal to the integral from 0 to tau of alpha, and play around with the integrals and the derivative. I don't want to prove it because it's a bit long, but it's nothing too deep. Once you have the ingredient set up, you just have to be patient and compute derivatives and do estimates. But yeah, so these are the keys estimates. So every time you can prove that your shear is linear and your distortion is t to the -1 of order t to the -1, then you are in good business to continue. And something like this happens also for other smooth parabolic flows, so not just for Horocycle flows. Yeah, so because to prove these kind of estimates, you don't really need any fine control on the ergodic averages. These are to prove these estimates, we do not need the estimates on the ergodic averages that we proved in the second lecture. It's softer, and they are enough. Okay, so let's assume the proposition and prove mixing. Okay, let me assume that t is sufficiently big, so bigger than all the constants that have appeared so far, that I always called a, but okay. So this is the integral that we need to compute. Okay, and I would want to do a change of variables as we did, so I multiply and divide by the derivative, because I want to do a change of variable, and so I want to change a variable, I need to have the derivative, but I've also multiplied by 1 over the derivative, and control the 1 over the derivative, is where the distortion comes into play. Okay, so I multiply and divide by the derivative of my parametrization with respect to S, and I do an integration by parts. So one function being this one over here, and the other function being 1 over the derivative. So if I integrate by parts, I get 1 over the derivative at the endpoints. In this case, I'll just take sigma, the other endpoint will be 0, times the primitive of this function over here, minus the integral of 1 over the derivative of this term over here, minus the derivative of -1 over this, I call u being the distortion, so I just write plus this distortion coefficient, times, again, the integral of this function from 0 to s, integrating now in s, okay, integration by parts. Okay, and now in these integrals that appear here, I can do a change of variables, because that's what I wanted to do. So if I do a change of variable in those integrals, I get 1 over the derivative of my parametrizations, integrating between tau of Tp and e to the sigma tau of T sigma, my function f along the Horocycle. So this term over here is really the integral along this curve over here. And then I have the other term that has the distortion and the same integral up to some smaller s. So now I use the estimates I stated for the shear and the distortion. So this term over here is going to be 1 over t. And this term over here is also going to be bounded by 1 over t. And I also, I will also just shift the extreme of integration. So here it will appear an integral from 0 to the difference of the two terms. This is going to be bounded by a constant over t times the supremum over all possible s of this integral over here. So where I start from the point h alpha t, so the first point over there. Okay. So how large is this? So this is an integral from 0 to this quantity over here. So how large is this quantity? Well, so the difference of these two is definitely bounded by s times the derivative at some point, and the derivative at some point was bounded by a constant times t. So this is going to be at most a constant times s times t. Okay, so I can use so this is a nice ergodic integrals for the Horocycle flow. parameterized in the natural way up to this time over here. So I can use the estimates that we proved for estimating the ergodic integrals. And I get that the quantity that I wanted to estimate from 0 to sigma is going to be bounded by some constant, the norm of the function, times sigma to the 1 minus gamma times t to the minus gamma. Maybe I did forget the sigma in this formula over here. So it's going to be this to the minus gamma. So I get sigma to the minus gamma, t to the minus gamma, and I think I forgot the sigma before, so I get sigma to the 1 minus gamma. Okay. So to conclude, I needed to estimate this term where I had 1 over capital S in front. So we proved that it was bounded by a linear term in S that was given by the error we committed when, instead of taking this segment, I was taking the segment on the Horocycle orbits. And the error here was S, and I'm choosing S again to be t to the minus gamma over 2, so that this term is going to be t to the minus gamma over 2. And the bound coming from the ergodic integrals over here is going to be S times t to the minus gamma. So the gamma here divides with this S over here. And again, so here I have S times t to the minus gamma, and I'm choosing S to be t to the minus gamma over 2. So I can also bound this term definitely from above with t to the minus gamma over 2. So I get that this term is bounded by some quantity that decays polynomial in t. So what we proved is that indeed the time changes of Horocycle flows are also mixing with polynomial rates. What we proved is that, again, there exists some positive constants such that for all sufficiently smooth function and all time big enough, the correlations can be bounded by a product of a constant times a product of the norms of f and g times some negative power of gamma. And okay, if you trace back our argument, we were a bit brutal in some estimates. So here, for example, we choose gamma over 2, where gamma was the exponent coming from the equidistribution. So the exponent we got was half of the equidistribution exponent, which is not optimal. If you try to be more careful, you can get this to be exactly the exponent of equidistribution. But in any case, we do not expect this method to give us the optimal rates. What we can say is definitely, though, that the mixing rates are polynomial. And maybe
using this method, gamma is always lower than 1/2.
Yes, it's at best 1/2.
So absolute spectrum is not in the range of the spectrum.
It actually is for a trick. Okay, give me 1 second and I'll come back to your question. I just to add some comments about this theorem to attribute. So the question about whether time changes of Horocycle flow are mixing is some history. So in a qualitative way, so proving just that they are mixing, I think was proved by Kushnirenko and Marcus. Kushnirenko had some additional condition, and Marcus proved it actually in not just for time changes of Horocycle flow. His argument is very general. But the assumption he has basically are just that you can take derivatives of the parametrization that you get when you do this argument. So Marcus' argument was really this shearing of geodesic segments, and his assumptions were the very minimal ones that you need to be able to take some derivatives in appropriate directions. And they do apply also, I think, to some non-constant curvature cases. So it's much more general. The argument I presented here is due to Forni and Ucigrai, who proved exactly in our setting, so in compact quotients of SL2R, that time changes of smooth time changes of Horocycle flow are polynomial mixing. And then, okay, I generalized it. How? Well, also to consider non-compact spaces. So maybe SL2R, you are interested in time changes in SL2R mod SL2Z, and maybe you are not just interested in SL2R, maybe you want to go to SL3, SL4, or something like this, and so you can prove the same. And what is the, maybe I just mentioned, the step to go from the compact case to the non-compact case. In the non-compact case, recall we don't have our uniform upper bounds on the ergodic integrals, right? There are orbits that do not equidistribute at all. But and maybe this is why I stressed it a bit before, in the mixing via shearing argument, you just need L2 estimates. You don't need to prove that all the push forward of all curves equidistribute. You just need to prove that in L2 they equidistribute. And so that is sufficient for mixing. And to prove that statement for the L2 norm, or maybe you're allowed to discard some polynomially small set of points that do not equidistribute. To have a statement like that, it's enough to have polynomially mixing estimates. So once you have polynomial mixing, you can prove L2 bounds on the ergodic averages. And with those, you can run the mixing via shearing. So in the work I did here to prove this generalization, the key observation was that to prove this mixing via shearing, L2 estimates are enough, and to prove L2 bounds on the ergodic integrals, it's enough to have quantitative mixing.
So you have quantitative mixing for the unchanged flow, the usual flow, and that gives you deviation of averages, good L2 deviation of averages for the unchanged flow, and then that gives you rate of mixing being shearing for the changed.
Exactly, precisely. Okay, so now I'll come back to your questions about absolute continuous spectrum. And this was done also by Forni and Ucigrai. So the observation, again, is that to prove absolute continuity of the spectrum is enough to have mixing estimates for a dense subset.
Okay.
Exactly. And so to estimate ergodic integrals, we did it for smooth functions, but if you limit yourself to coboundaries, this stuff is going to be bounded by a constant. And you have a divided by t in front. So this was their insight. And this is done also in other cases where, again, if you want to prove absolute continuity of the spectrum, usually you run the mixing via shearing argument, and then you choose your functions to be coboundaries, so that when you have the equidistribution of orbits, that's the best you can have, like coboundaries. Yeah, you get the 1/t that is in L2, so this gives you this.
Yeah.
Okay. So I finished talking about the Ergodicity mixing properties for Horocycle. Other questions? Okay, I'll start. So. Okay, thank you. Okay, so probably to conclude this mini course, I want to talk about a natural question that arises. Namely, are these time changes, are they really new flows, or maybe they are just the same old flow in disguise? So I want to talk about the isomorphism problem. So if I give you a smooth time change of Horocycle flow, is this isomorphic to the unperturbed, the standard homogeneous Horocycle flow? And a very striking result, I think, was proved by Marina Ratner, who proved a very strong rigidity result. I will state it. I will not prove it because it's a very hard and long proof, but I will try to give I will do two things. I will prove a very baby version of the theorem, and this I will do by hands, and then I will try to give one idea behind her result. But the idea would be done by pictures. So, but hopefully it will convince you of at least what's the insight. Okay, so let us talk about the isomorphism problem. So same setting, compact quotients, and time change generated by a smooth positive function. So this is just a recap. So the natural question, as I was mentioning, is I give you a time change. Maybe there exists some measurable automorphism from your space to itself that sends the invariant measure for the time change to the invariant measure for the unperturbed flow and makes the diagram commute. So if you apply the isomorphism and then flow for the standard Horocycle flow, it was the same thing as flowing with the time change and then applying the automorphism. So it's a measurable change of coordinates that tell you that these two flows are actually the same flow, at least as far as the qualitative ergodic properties of these flows are concerned. Okay, so is it possible to determine which time changes are isomorphic? The isomorphism is continuous, decay, or smooth if this map psi is going to be continuous, decay, or smooth. So if you have isomorphism, you can ask about the regularity of the isomorphism. Okay, and we will talk about, so there are, one direction at least is easy. So there are some cases where I can tell you that yes, the time change is going to be isomorphic to the unperturbed flow. And this is related to the notion of coboundaries that in some sense we also saw earlier today. So I would say that the function is a coboundary for the Horocycle flow is if there exists another function g such that my function, I can write it as a derivative of g in the direction of the Horocycle flow. So a coboundary is just a function that is actually a derivative of some other measurable function. And a function is an almost coboundary or is homologous to a constant if the function is given by some constant plus a derivative of another function. And you will say that my function f will always be sufficiently smooth, but in some cases, the function, even if it's smooth, you can have a solution to this equation where the function g is less regular than the function, and usually you have a loss of regularity. So when you say stuff like it's a measurable coboundary or it's a C1 coboundary or a continuous coboundary, you refer to the regularity of this function g. Okay, now there are, what do I mean by the regularity of the function g? Why am I talking about the function g? Well, as an exercise, you can verify two things. Well, if a function is an almost coboundary, so if it satisfies something like this, well, then necessarily this constant c needs to be the integral of the function f. Just recall that if you integrate the derivative, you get 0. And if f is a coboundary, so if there exists a function g that satisfies this equation, then all other g prime that satisfy the same equation differ from g by a constant. So this you can prove as an exercise. And again, the key thing to remember is that the Horocycle flow is ergodic. Okay. So why am I talking about coboundaries? Well, there is we can verify that if the function alpha that is inducing the time change is an almost coboundary, so if it is homologous to a constant, then the time change is actually isomorphic to the unperturbed flow. And the regularity of this isomorphism conjugating these two flows is the same as the regularity of a transfer function or any transfer function because they all differ by a constant. And I want to finish by proving this lemma. So I think I have 5 minutes. Okay, so let us assume that our function alpha that induces the time change is an almost coboundary. So by definition, alpha minus a constant, the constant needs to be the integral. So alpha minus 1 is going to be the derivative along the Horocycle flow of some other function beta. And now, as a I would define my isomorphism to be this map over here. So at the point, you flow in the direction of the horocycle for time given by the value of this function beta. So I am defining this map. So from this definition, it should be clear that the regularity of this psi is going to be the regularity of this beta. And now I want to prove that the map that I define in this way is an isomorphism between these two flows. So what is this isomorphism? This isomorphism is just a push along the horocycle orbit. So the map is just you move the point along the horocycle direction for some times that is given by this. Okay, so recall that our definition of tau was that t was equal to the integral from 0 to tau of alpha. And now instead of alpha, I write 1 plus u of beta. This was my assumption. So the integral of 1 is going to be tau. And then I have the integral from 0 to tau of u of beta composed with the flow. But u is the derivative along the flow direction. So I can rewrite this integral as the integral of a derivative of beta. Does this make sense? So u was the derivative along the flow direction. So this is an integral of a derivative. So by the fundamental theorem of calculus, this term over here is going to be beta at this point over here, beta at h at tau, which is also beta of h alpha t of p, minus beta at the initial point, beta p. Okay, so if I use this equation, I can verify that psi composed with the h alpha t. So by definition, this is psi is h of beta at this point over here, composed with the ht of p. And now h alpha t, I can write it as h of tau tp. So here I have t pushed by tau tp and then by beta at this point. And now I use that beta times tau is equal to t plus beta. I'm using this equation that I proved over here, prove this second to last equality. So you have h of t plus beta of p. And this by definition is h of t composed with psi of p. So at least I verified the commutativity of the diagram. So if I switch my point of view and I think of the unperturbed flow as a time change of my time change given by induced by alpha to the -1, I can repeat the same argument the other way and find that the inverse of psi is going to be a push along the time change function of minus beta. Okay, it's an expression for the inverse of psi is pushing in reverse with beta, but with the time parameterized by the time change that now I think of as the original. Does it make sense? I think I'm getting tongue twisted, but yeah, okay. So it's an automorphism. I mean, we have a nice expression for the inverse. So psi is a measurable automorphism, and the last thing we need to verify is that it sends the invariant measure for the time change to the invariant measure for the Haar measure. Oops. Okay. So how do we verify this? Well, we verify by looking at continuous functions. So by unique ergodicity, for every point p, in particular for psi of p, the limit of the ergodic averages of f will converge to the integral of f with respect to the Haar measure. This is by unique ergodicity. So apply to the point psi of p, it is true for every p, so it will be true for psi of p. And now I use the commutation of the diagram that I proved before to rewrite this function here in the integral as f composed with psi composed with the time change. Okay. And now we proved half an hour ago that this ergodic average over here converges to the expected value, and the expected value is the integral of this term in brackets, so f composed with psi with respect to the invariant measure for the time change, that is this vol alpha. And by definition, this is the push forward of vol alpha with respect to the automorphism. And this equation here is true for every continuous function f. Therefore, these two measures are the same measure. Does this make sense? Okay, and okay, so this gives us one direction, and now we would like to prove the other direction, that all isomorphisms are somehow coming from isomorphism discord. And so next time we will discuss a baby case of this result that we can prove by hands, and then I will give some ideas, state and give some ideas behind Ratner's rigidity results. Okay, I'll stop here. Thank you.
Focus with electrical computation. When you're considering the ergodic averages, you somehow transform these for the time change to something of the usual. But in the mixing part, you went already directly to the method of the proof to prove mixing. If you take the decay of correlations and you try to relate this decay, just like the decay of the usual one, the decay of the time changed, the other one. What goes wrong? I mean, like, why in the ergodic average you really can't just relate it to one and the other one?
Because in the ergodic average is basically I'm fixing one point.
Yeah.
And so because so globally I cannot write that if I move a whole set with the time change, I cannot. It's very hard to write as to move the same set with the unperturbed flow because the movement can be very, very different. So remember that the difference in the parametrization is sublinear. So if I move it for a large t, one point can be super far away with respect to the other. So look at sets is hard. I don't know if this is a good answer to your question.
Yes.
Or at least it's unclear how to directly work with the correlations. What we did was basically looking at what happens. You fix a point and then you work with that single point. So everything was easier to control. Maybe it is possible, but I am not aware of any argument in that direction. So, yeah.
You have any questions? Not? Let's take that again.